Today, I had the pleasure once again to speak with James Douma, who I've actually introduced as an expert in some areas, but now I'm just going to say he's an expert in all areas in terms of tech, because he knows everything. And beyond that, he actually knows all about physics and the origin of the universe and everything too. So if you're interested in a wild ride that goes from AI Day #2 all the way to the origins of time and the universe, stick around. It's going to be a lot of fun. Hey, y'all, it's Dr. Know-It-All. I am very, very fortunate to be with James Douma again. And I was going to say you're like an AI expert, but I think after watching all the Dave Lee interviews and stuff, I'm just going to call you like the expert on everything at this point, which actually leads me to question numero uno.
Dr. Know-It-All Jr.
I know you're the senior. I should be handing my title over to you is what I discovered, because the whole thing with Dojo, I was like, oh my gosh, I learned so much more from you talking about it than the original show, just because you had time to go into more detail. But I want to start off with the first question, which intrigued me ever since AI Day. And we had a very, very brief moment. It was kind of like drinking from a fire hose while we were there. And so I was like, oh, hey, James, and then like on to the next booth or something. But anyway, what was the topic during the presentation that you had to stretch your brain the most to understand? Like, it seems like you just know everything. And so I'm kind of wondering if there was a moment where Dojo was my moment, where at the end, it was after like the whole time and it was the end. And I was just like, I can't take in any more information.
Most of it, I could integrate on the fly.
Okay.
That's my superpower. Like, I went through college and I've never taken notes for anything. I just sit and watch, and I really pay attention, and then I just absorb it as I go in. So I try to fit what I see into the. So the one thing, when the language of lanes thing came up, and I looked at that, and it wasn't clear to me how, the language of lanes, it's a catchy term. They're using a sequence model that does sequence to sequence stuff. And in a sense, so my understanding is they're using, what would be a language model, right? And this technology, which is highly developed, right? There's lots of work on language models and sequences. So that's a technology that you can take off the shelf and you can make good use of it, like right off. Anyway, so how do you, what exactly are you getting when you take a set of node traversals for an intersection and turn it into a sequence and then run it through a language model? And so that was like, I didn't get that on the first pass. I had to rewatch the video and think about it some in order to like grok what they were doing there. Right. Everything else pretty much worked for me. Gotcha. So, but a lot of this, with the first AI Day, Dave and I had talked about it, and I spent a lot of time thinking about, what they might do or might not do and all that kind of stuff. So for me, the first AI Day was mostly, they did do that and they didn't do that. Like, I'd already thought through most of the things that were there. So I didn't really have to figure that out on the fly. This time there was stuff that I didn't expect to see. And so I had to think harder about some of the stuff. It was also a lot denser. I feel like the first AI Day, the level of technical sophistication that the audience had to bring to the material in order to get something out of it was significantly higher, I feel like, this time. And more than that, it wasn't sufficient this time to just have a broadly good understanding. Like, on the Dojo stuff, they had 3 or 4 different, things they talked about on Dojo. And on each one of those, it was really helpful to have a specific familiarity with that particular problem that they were looking at. Dojo, for me, is the easiest thing because, I'm used to design electronics, and I worked on clusters and high-speed communication systems. And so that stuff and thermals and all that kind of stuff is stuff that I had to deal with at jobs that I did. The AI stuff works for me because that's been like what I spent most of my time on since 2007. So, and then, there's other stuff too. The robotic mechanicals, I used to work with mechanical engineers to design I don't know what the sort of a high performance 3D transmission structures for electromagnetic energy. And so I was really familiar with how like the process of doing that kind of stuff works and the mechanics and whatnot. When I got into Tesla, I spent a bunch of time sort of trying to understand the process by which electric motors were designed. And so I thought the actuator thing would be super interesting, but that's probably the thing that's hardest for me.
Interesting. Okay.
Probably just at a fundamental sort of tech thing, because I have a certain amount of industrial experience with doing that stuff, but not a lot of stuff that's specific to the problems that they're working on.
Right. Right. Interesting. Wow. So you were almost the perfect audience member for them. Somebody who actually knew enough about all of the areas. Cause like I was like good on the software end of things, but the hardware is a real stretch for me. So
the event wasn't really set up for a generalist. I'm a generalist, right?
Yeah.
Like I cover a lot of stuff, and I cover it to enough depth to integrate it into what I know. But there are relatively few things I go super deep on. Like that was what I did professionally, and that is what I've done in my hobbies. So generally, I would have thought that would have been a good event for me. But the downside to it is that the event is basically designed for people to come in, have this particular piece of the presentation that they're really interested in, and then go find the people that are into that piece and talk to them, right? Whereas I wanted to start at one end of the booths and do the whole row, and there were like, what, 20, 30, 40
I know. It was actually very frustrating. As soon as we got in there, I started at the dojo one and started working my way down, and I only got to the edge of the other side before.
I got through like 4 booths or something.
Yeah, it was very sad. I was like, speaking of which, that brings up question number 2 I wanted to ask you, which was, if Elon Musk like granted you like full disclosure of something, which team would you pick and what question would you ask if they, had to answer you completely? So that, because one of the frustrating things, of course, was going to the booths and asking them a question, and they're like, oh, I wish I could tell you more. I'm like, I got to stop because I can't talk about it anymore. But what rabbit hole would you like to go down if you could explore one area?
I have competing priorities there. Like there are the things I'm curious about.
Right.
There are the things I'm curious about because I know a lot about them, and and I have a very specific question about how they do things. Right. There are things I'm curious about because I don't actually know a lot about them, and I would like to know more, kind of broadly. Right. So that would that's a thing. Battery chemistry would go in that. Like I don't know a lot about battery chemistry, and so that would be a really interesting thing to people to talk about. Then. But I think, as an investor, I would want to go for the thing which most directly impacts my like, what is the thing that's most important to my investing thesis that I don't know that I could know if I talked to somebody inside? And that would probably be battery related. Like, I don't, for me, there aren't, the biggest variable in the investing thesis in the next like 5 years around Tesla is going to revolve around how quickly and to what degree FSD performance ramps. Right. That because I think there's enough inertia behind the big scale stuff of the business, like that you can extrapolate forward on the say the production curve. They've built a certain number of factories. We've seen them do this kind of stuff, and you don't know perfectly how things are going to turn out, but you can probably predict within like 20 or 30% going out 5 years or something like that with relatively high confidence. That would be your 50% error kind of bound on that kind of stuff. I'm actually extremely confident about FSD. And Elon said on the conference call, it's 100% going to happen. And I'm right up there. It's definitely going to happen. So once you put that thing away, because it's shocking to me that the conventional wisdom still is that you need to model Tesla assuming it's not going to happen. That's what all the analysts do, right? People are extremely reluctant to build a model based on that. But then, so setting all that stuff aside, if you're really confident about FSD and you feel like the core part of the business is pretty predictable, well, what's the last big variable that you would like to understand? And the answer is ramping battery supply, I think, So what is it? The limiting factor, right?
Right. Exactly. So, good name for a YouTube channel, by the way. But I mean, I agree with you. Yeah, it just seems like that would be the big thing, but also there was a weird little bit of information that we got that the semi truck is actually starting with. He said not 4680. Everyone assumes it's 2170s. I mean, who knows? It might be 8650s, whatever. 1860, yeah, 1860. Anyway, who knows what it is? But it's not 4680s, which seemed a little unusual. But in the kind of trade-off, I guess, is that those smaller batteries don't have as much heat issues. So maybe, at least my understanding, again, because it's not perfect, but that you're giving up some of the density so that you have to have more weight in your packaging, but you're getting back some advantages to having smaller batteries. But it could also just be the fact that they haven't ramped the 4680s as fast as they wanted to. Like,
I would guess it would be at 4680 supply in the
Right.
I mean, you know, everything's going to migrate to 4680s given some time, because that's just going to be the most efficient platform. And the thermals on the 4680s are good because essentially it has a really good thermal path to the can because of the tabless electrode, right? So like the thermal path in regular batteries is not great, just having that single tab. But 18650 is like the volume to surface ratio on them is much better than a 4680. So like if you're looking at it, it's always been funny to me that people, there's sort of this presumption that the 18650s were an inferior battery compared to the, you know, the one that gets used in the 3 and the Y, and that's just not true, right? It's because you can use the same chemistry in both of them. The form factor doesn't inform the chemistry a little bit, not much, but because it informs it to the extent that the thermals inform that kind of stuff. But what you learn on the you know, the bigger battery you can apply to, and the thermal performance of the 18650 is just going to be better than a tabbed battery that's physically larger.
Right. Yeah, and I think, I mean, that's the likelihood is that's why the Plaid X and S still use those smaller form factors, because they're drawing so much ridiculous amount of current as they operate.
And they have the capacity. I mean, the thing is, they have this 18650 supply, which is proven and stable, and like why it's not a matter of taking those machines and switching them to a different form factor, right? Like that's not how a battery line would switch over. You get rid of those lines and get new lines. So why would you ever get rid of battery lines right now? Like if you have a working battery line, let it work, you know, change the chemistry a little, you know, up the yield and that kind of stuff, but don't get rid of a battery line. Why would you do that?
So I guess it probably makes sense that as they transition their vehicles to 4680s, they'll take those other battery lines and start dumping them into like energy storage or something like that, potentially. Because the advantage of the 4680 primarily is that it's easier to build these structural packs, which makes the cars lighter. There's advantages to that are unimportant on a power wall because it's sitting on the ground. You know, it doesn't matter if it weighs a little extra or takes a little extra volume.
I mean, you could do structural packs with smaller cells too, right?
Yeah, I guess.
I mean, the 4680, the can, and we actually, I haven't heard what the can thickness is on the latest version. Some of the early ones, you know, there was speculation that the can thickness was contributing to the rigidity of the structural pack. My read on the construction of the structural pack is it does not rely an awful lot on the thickness of the metal. You know, it's a packed honeycomb. It's a filled honeycomb. Right.
And then whatever that pink
stuff, a lot of steel
is,
to be incredible.
Yeah, whatever that pink stuff is, they inject into it is incredibly stiff. I mean, Monroe and Associates had a hell of a time getting that stuff off.
that pack is going to be so unbelievably stiff. It's just crazy. So I don't know why they had so much steel on it. Another speculation was that the combustion, essentially, if you make the can strong enough, you can dial down the layers of additional fire prevention structure that you have to put in the pack, because individual cells would be capable of isolating themselves to a more effective.
Right.
And that seems wrong to me, but it's like, I don't know what the burst pressure on a can, steel can that size is. It might be really, really high.
Yeah. Jeez. There's so many factors that you have to take account of when you're making batteries, because I think, I think there's a tendency for people to forget about how much energy is in those things. Yeah. You know, when you charge those things up, they have a lot of potential energy inside them.
It's impressive.
Yeah.
That I mean, the Optimus, right, has a 2.3. Let's see, 2.3 kilowatt hours. It's what, 33.6 megajoules per kilowatt hour. So that's what, 8 megajoules, right? Is that right? Yeah, 8 megajoules. Divide that down to calories, and you got it's 4.184 calories per joule, right? So that gives you 2,000 kilocalories, which is that's a human calorie budget for a day, right?
That's a fascinating comparison. So that means that in some ways, aside from the inefficiency of growing food for us humans, Optimus needs approximately the same amount of energy that we do in order to function. So that's fascinating.
Yeah, no, it's pretty impressive. And one of the cool things, I mean, animal biology is crazy efficient. It's really, really efficient. And but the thing is, electric motors and actuators, properly done, they also have extremely high efficiencies. And so, but they've got an Optimus robot that's roughly human scale, it's roughly human mass, it has roughly the same range of motion, it has roughly the same sort of physical strength. It's a ballpark, right? It's a little bigger, it's a little smaller, maybe it's a little heavier and whatnot, but it's using one human standard diet's worth of energy to do its stuff during the day. That's remarkable. I mean, how many airplanes aren't as efficient as birds are, right? No,
not at all.
Submarines, they're not as efficient as fish are. It's pretty impressive. You can build a humanoid robot and be in the same class. And humans are pretty efficient, right? That's from a mobility standpoint and that kind of stuff. It's a funny design that we stumbled, because we started out as quadrupeds, right? And then primates, whatever it was that we got to this shape. It was a series of kind of fortuitous accidents, maybe. But it's a great, human beings are the second most efficient land animal in terms of calories per kilogram per kilometer of transit. And the thing that beats us is the kangaroo, right?
Really? I didn't know that. They seem so inefficient because of the hopping. That seems like a very inefficient.
Yeah. So it turns out that the tail is a spring that stores kinetic energy as they move along, and it has really high recovery.
Gotcha. Yeah. Did you have you ever read the book Born to Run? It's a fascinating. Okay. So it goes into the theory of human consciousness developing because we were persistence hunters. The whole advantage that humans had before we had tools and other things was that we could keep going for a really long time, whereas we would just wear the other creature out, right? So if you've got an elk or something that you're chasing down, you don't have to outrun the elk. You just have to keep it moving until it exhausts itself. And so
you have to outrun it on the scale of a day or two. You don't have to outrun it on the scale of an hour or two, right? Right. As long as you can keep track of it.
Right. Exactly.
Because it can't outrun you in the long run.
Right. And of course, that's predicated on a group hunting strategy as well, which is so group hunting and the fact that you had to project your mind into the mind of this creature and understand what it was going to do next. That is his contention. And again, it's anecdotal, but the contention is that our consciousness derived from the fact that we had to communicate with others and project our consciousness into these other creatures to understand their behavior and to understand what they would do as we hunted them in order to effectively hunt them. So it's a really fascinating book. It's
modeling prey animals is pretty important. It's been a while, but I remember 20 years ago reading interesting stuff about predators' ability to model the behavior of prey. Right. So leopards being able to model deer or whatever.
Right.
Which actually, I live in a place where we have both mountain lions and lots of deer. And I can tell you from interacting with deer that they're dumber than squirrels are. They're the dumbest thing ever. So I'm a lot less impressed with a leopard's ability to outthink a deer now that I've had to
live amongst them. Yeah, actually, nope, I don't see them right now, but we have woods behind our house and they hang out right by the fence there. So yeah, they're not the smartest creatures in the world, but they're big and they can actually, you know, those hooves, they could hurt you if they hit you. So obviously you want to be careful as a predator that you don't get.
Yeah, where I live, we have a lot of bears and the occasional mountain lion, and we also have bobcats and all, you know, that kind of stuff. Right. And people are often like, aren't you afraid of the bears? And I've been living in this house for 30 years, and like, you know, I encounter bears like not every day, every week or something like that. Right. And I've never had one bother me. Right. But every time mating season runs around, I get some guy with horns who wants to, you know, I go down to get the trash and he thinks I'm coming after him. Right. Those people worry me.
It's the hunters that you worry about more than the hunted stuff. So, yeah, that's pretty crazy. Wow. That really, I'd never really done the calculation about the 2.3 kilowatt hour battery pack, but that is, I mean, first of all, it's really impressive that the Tesla is able to be that efficient. But secondly, it's really, it creates a fascinating idea of what the minimum energy requirement to be a human being is. Like if you're going to be an active human being and eat an adequate number of calories, like it seems like it's on the order of 1,500 or 2,000 calories a day in order to function. And even a humanoid robot is going to need pretty much that amount of calories. So that's really cool.
And you store it in fat and glycogen, and if you work out the density, fat is 3,500 kilocalories per kilogram, I think, something like that. So I think that's, you know, it's roughly the same sort of density.
Right. We got our little batteries, and the older I get, the more batteries I have. Wow. Yeah, I've actually cut out sugar in actually since Tesla shareholders meeting. I ended up getting COVID after that and lost my sense of taste. And I was like, okay, I'm cutting sugar out because I can't taste it. And it's been fascinating not having that in my diet. It's been an interesting like evolution of my bio. Like I could feel the difference between a couple of months ago and now. So anyway, interesting stuff. So back to AI Day, like, was there anything that surprised you? Because you said last time around, certainly Optimus surprised you a little bit at the first AI Day, right? The fact that they announced it, or had you already modeled that out as a possibility? Just the fact that they'd make a humanoid robot.
Yeah, I mean, a lot of aspect. I mean, they told us approximately what it was going to be before. You know, it's going to be Elon's. Actually, it was a little bigger than Elon predicted it would be, which it is also predictable because it's hard to make. It's easier to make things big than to make things small, right? Let's see. I was a little surprised that they went with 5 fingers. I mean, it's great, right?
Would you have gone with 4 or 3? Like a hand like that or a hand like that?
To figure out the right answer, you have to decide what tasks you want to do. But like generally the tasks that benefit from having that additional that pinky finger are not a big selection. But the way that they designed the hand sort of makes it make more sense, because I didn't expect them to put the actuators in the palm. That kind of surprised me. Like one of the things that's complicated about doing humanoid robots is generally you want to put the power for the actuators in the forearm, right? And then have some kind of power transmission system that runs through the wrist. That makes the wrist pretty complicated. And that's actually one of the trickier things about making a dexterous human robot, is figuring that out. And they just punted on it. They made the palm fat, and they used small actuators. So. And then they had to do with, you know, like a tendon or whatever. Like I didn't expect that. In retrospect, like it's a good solution. I wasn't thinking in that direction. But the thing is, if you do put the power down here and you care more about the power grip, they have they didn't give us grip strength, but they told us carry a 20-pound bag. So say roughly 20-pound grip strength. That's a little on the low side. Like it's plenty for doing most of the tasks that you're going to want, because they're not going to want carrying really heavy stuff around in the early stages anyway. But, you know, I mean, human hands are really powerful, insanely dexterous. They have many degrees of freedom, and they have a lot of feedback sensors built into them. And all of these things contribute to the dexterity of human beings. In the short run, like in the next 5 years, dexterity for Optimus isn't going to be super important, but to really fully exploit the potential of a humanoid robot human form, you're going to want the dexterity, the sensitivity, and you're going to need the power and all the other stuff that human beings have. So I think, solving the hand and solving it really well it's a very substantial mechanical engineering challenge. But I expect there to be a lot of progress in that space, and at some point, we'll get that. So
Gotcha.
I wasn't expecting them to make a lot of progress against what I see as the ultimate goal. It's amazing that they have a robot at all. Like designing a humanoid robot from scratch and then building it, including custom actuators and stuff in 9 months, however they did it. That's phenomenal. So I was fully prepared to go there and have them, this was as far as we could get.
Right. It can do this.
And that would have been fine.
Yeah. Interesting. So you didn't happen to catch that video that I did with Scott about Dennis Hung and his work with Romella?
The first one I did. Yeah.
It was from 2014. Anyway, it turns out we discovered a paper and a video that he had done with oh gosh, what was his name? Thor. But a lot of the constructive, not the hands at all, and certainly not the vision.
The 4-bar link for the knee, right?
Yeah, the 4-bar link for the knee, the way the hips and all that stuff work. But of course, all custom built actuators, and not the kind of stuff that Tesla's doing where they're trying to mass produce this eventually. That was the thing that really, really blew my mind. Was I liked Bumblebee a lot because he just had little flashy lights all over him, and he was obviously a one-off kind of thing that's very, it's the thing that you're tinkering in the shop and soldering things together and, holding it together with duct tape, trying to hopefully it stays together.
Well, you have to build something for the software guys so they can
exactly. Yeah. So, but the first, the AI, I think it's called AI2. I think that was the name of the other one, but that one looked so elegant in terms of the capability. I looked at the hands really closely because we could go up and take pictures afterwards. And so I was pretending I was taking pictures and going oh, but I mean, it's just elegant. There's really nothing in the fingers. They're just hollow with a metal cable running through them. So very simple.
It's the structural members I like. I thought it's a very aesthetically pleasing shape. I agree.
Yes.
And they did a great job so this is one of the things, there's so many different ways that you could say design the structure of the lower leg.
Right.
You could take a lot of different approaches in terms of what do I want the actuators to do? Are they going to be structural? Are they not going to be structural? Where are the hinge points going to be? How much twisting load do I need? You do a bunch of modeling to figure out what that is. And then at the end of the day, you 3D print, the minimum metal structure that provides all the loads that you need and which can house the actuators and stuff. And it's really cute. I mean, it's nice. It's good looking, and you can see how it does the job that it does.
Right.
So I didn't get a chance to look at the thigh or the pelvis or whatnot very closely. The torso is easier in a lot of respects. And it's also constrained. They put the batteries in. The batteries seem to be in a cast housing, right?
Volume. Yeah.
So they're using that for structure. For the structure for the torso. It looked it was not. The details were hard to predict, but the rough. The rough outline of what they were going to show us, we kind of knew. So
and I mean, there was two things. Number one is kind of the MVP, the minimum viable product that you can get, but and you could see the compromises they made, like you said with the hand. It's this is an utterly simple hand that can basically do a grasping motion. It can't do this. I mean, it could do something like this where it can have a trigger, but it's not going to play the piano. It's not going to play the guitar. It's not going to do things like that, but it can pick up a power tool and it can pick up an object, most objects. So so that's minimum viable product. Then in the leg, the really fascinating thing was to go back and look at the video that Dennis and his students did, the Romella Thor robot, and how the range of motion was really big. And Scott explained, I think it's called a Carmen joint that has incredible mobility and everything, and how Tesla basically replaced it with a ball and socket joint. So you could see them reducing range of motion, reducing all of these things to make this thing really simple to build. And it looks to me like it's going to be mass producible Like,
And so
I don't know
they
how
have-
complicated the actuators
They have
are.
like 90-degree range of motion on the knee.
Right.
We're talking about the knee.
Yeah,
Okay.
well, the knee and the hips. But the
Okay.
Romello one actually had, I think it was 135 or 140. It was huge. It could actually do a running motion. But
Yeah.
but what robot's going to need to run? I really hope the robot doesn't run, or else that's terrifying.
Yeah, I think Elon considers that a bug and not a feature.
Right, exactly.
The robot can run.
So, you know, but we're looking at something that's restricted in its capabilities. And so why build out all this extra stuff that costs a lot of money and is very difficult to do? And, you know, and they showed us the actuators too. And I thought, okay, we've got it down to 6 actuators that they have to build for the body of the robot. That's excellent. You know, each one is not its own custom actuator. It's like, no, this will work for both.
The envelope is really good though. They got really good coverage out of 6. Like I seriously doubt that there would be a significant performance advantage. I was surprised. I went back and looked. I was talking to Scott about this. They use planetary rollers in the at least in the midsize actuator. That was the one that they showed us a cross section of. So it actually has negative gearing in it. And when I first looked at it, I assumed that they would be gearing down the motor, right? Because it can be hard to get as much linear force as you want out of a linear actuator that you're using in a body. The more force you can generate, the simpler it is to design the body. But they actually went the other way. Like they weren't limited in the force, they were limited in the travel that they could get. So they changed the physical form factor to make the actuator thicker so that it could generate more force, more torque. And then they went, but when they went thicker to a shorter body, they didn't have as much stroke as they wanted. So they put a planetary gear in that gears up the stroke so they can get twice the travel out of the same, which that was, I mean, you know, they have this design space and they figured out what they needed to be by doing a bunch of simulations, and then they ended up with that. But it just goes to show like how powerful electric motors can be, right? If you do a good job with them. If you get the tolerances way down, the force you can generate with an electric motor can be remarkably high. And that like both the magnets and the windings in those are like, that actuator is packed to the gills. Like there is no space in there. It's got to be conductive. There's no way you can blow air through that thing. Right. It's probably watertight anyway. So
yeah, I actually they let me. Did you pick up the Dojo chip, the tile?
No, I didn't.
Oh gosh. Oh well. Okay. So that was
like it was 19 kilograms.
Yeah. I guesstimated it was 23, but anyway, it was heavy. You know, those plates, the big plates in the gym that you pick up, it was kind of like along the lines of that much weight.
Well, like look, it's, you know, the top of it's a copper heat spreader, right? Like that is a heavy metal.
This thing is. Yeah. So anyway, the guy was like, you could pick it up, and I was like, okay, you know, third try, because it didn't look like it was going to weigh that much. So, you know, my wasn't ready for it. Actually, speaking of that, one thing that they didn't talk about at all was feedback. Like, and Scott has very particular ideas about that, but like, how does it know what it's doing? Obviously it can see, so it's got visual sensors, but you know, we humans, as we pick things up, we feel it, and we're like, oh, I'm pressing too hard because I can feel it pressing too hard or something.
Yeah, you get force feedback from position and back EMF. So the motors appear to all have force and position sensors. And some of them have a clutch in them. So they have 2 position sensors because you can declutch the input and the output. So they have force and position sensors. And then you can also, I mean, you can. I'm very interested in the potential for using the back EMF of essentially having an electromagnetic model of the motor, so that from the electromagnetic model of the motor, you know what the loads on the motor are, to save you having to add a separate force sensor. Because you know, that's how human beings do it, right? So but they have force sensors, and so if you're applying, you know, you can tell from force and position an awful lot about what the reaction that, you know, that the thing that you're picking up is. Like if you grab something soft, you get a certain amount of compliance, and so you look at the force versus position profile, and you get a before it stops moving, there's a rate
radius on the compliance curve, and that radius will tell you what the compliance is. And so humans do this also. Like our muscles are elastic and they have stretch sensors in them. So when you grab something and squeeze, one of the ways that your body estimates the force is how much is my muscle stretching. And but we also have the pressure sensors, and the pressure sensors in fingers are probably much more important for very, very fine motions, where the sensitivity of the elasticity of your muscles or whatnot would be there. So like if doing stuff like, I've always been amazed that like I can stick my hand in my pocket and I can count the change, right? That your model of the tactile surfaces on your fingers and the conformal geometry of your hand is sufficient to let you sort coins in a blind bag, and you can tell the head from the tail. You can feel I could hand you a coin that you've never touched before and show you the head and the tail, and you could put it in your pocket and you could tell one end from the other. Like your brain can convert the model of the geometry of that thing into what the tactile sensation will be to handle it and determine that. So to be able to do that, Optimus is going to need tactile sensors at some point.
But not simple ones. I mean, the most dumb one would be to just have one single force sensor, and so as it compresses, it's like, oh, more force. But our fingers have lots and lots and lots and lots of those little things. So
there are good designs out there for doing this, and somebody eventually. It's just that all of the examples of this stuff are laboratory curiosities, because we don't build robots that need it right now. So there's nobody mass produces that kind of stuff. But Tesla will for Optimus.
So that's interesting, because that seems like I kind of said when I looked at the not the Bumble C, but the other one, that I was like, oh, that looks relatively complete form wise, but it seems like the hand would be the most major place where significant changes will be made, like that a lot of stuff could happen and it could evolve into a much more dexterous hand eventually. Not that they need that now, but like 5 or 10 years from now, when they want to make a robot that'll play the piano.
There's a lot of potential for cost improvement too.
Yeah.
I mean, the actuators right now, they have a lot of parts in them, and that could come, in time, the actuators will be a major cost component for the robot. And so if you want to drive the cost down, if you want to make it for $10,000 and mass produce it, then, there are lots of small improvements are going to be necessary.
So going back, I'm wondering, because they didn't talk about the vision system or the neural network of the robot having control of this, but it would make sense that they would sort of fork a piece of the code off, that because of the compliance, because of the fact you've got cables, you've got a lot of slop in these robots, right? As it grabs something, it's not going to be millimeter precise or micrometer precise on exactly, it won't know exactly how much it's closed, because it doesn't have actuators inside of the fingers knowing exactly. So it seems to me like what they would do is attack that problem with a brain, which is the same thing we do. There's a ton of slop in our fingers and our arms and stuff. And we compensate with our brains, knowing it's like, okay, if I close it this much and I feel it, then that means it's closed the proper amount or something. So they didn't say that, but I don't know. It seemed like that was relatively obvious to me, but maybe I'm incorrect about that. I didn't know if you'd thought about that. Applying the Teslabot's brain to its proprioceptive elements.
They'll do that for sure. And I think in a lot of ways, so we are a little bit misled at how useful and effective neural networks can be, because vision is such a hard problem. Neural networks, mostly in the real world today, they get used in situations where you just can't do it any other way, because neural networks are kind of hard, right? So for the most part, we, language models, voice speech recognition, all kinds of things that just, you can't even touch them heuristically. Like we use neural networks for that kind of stuff. You can kind of do a lot of proprioceptive stuff with heuristics if you wanted to, but people who have used neural networks and who've trained them on robot bodies and that kind of stuff to calibrate motion for proprioception, like it works really well.
that they won't do that on day one, but it's not a tough problem. And for people who can solve vision, like proprioception is going to be easy for neural networks.
Yeah, we forget the rock stars that are working there, right? So it was actually really
hard.
Yeah. Oh gosh,
Vision
I mean,
is really hard.
Well, I mean, look at what percentage of the human brain is devoted to. It's like a ridiculous amount
like
of our brains.
Yeah,
it's like this huge chunk of our brain is the vision. So even for us, it's hard. It's not like something.
Well,
simple.
And there's probably. It's not like our vision system is going to be terribly inefficient compared to the rest of our brain. Like it's all evolved. Right. Vision is super critical, especially for creatures like human beings, where like our whole world is visual. Like it's how we interact with our environment and how we understand our environment. So our vision system is probably really optimized for efficiency. And so you can look at the rest of the neocortex, at least, because the structure of the neocortex is approximately the same, and say, yeah, vision is like a third of what your brain does, is just turning vision into something that your brain can understand.
Right.
So yeah, it's super, like by comparison, your language centers are tiny.
Yeah.
Right. No, and language is an amazing thing. Like it's really complicated. And I guess, to be fair, language in the human brain is mixed in with a lot of our executive functions and our like general, it's not concentrated into a specialized organ the way vision is.
Right. Well, obviously it evolved much later too, so probably just it's cobbled together from whatever parts it needed to be able to make it happen. So yeah, I mean, because everything has eyes. Past something like a worm or something, fish all have eyes. It's obviously a very, very important thing for creatures to have, is to be able to sense light and figures and things like that. So whether you're prey or predator. Oh wow. So speaking of that, let's talk about full self-driving a little bit. And I actually wanted to circle back to the language model thing, because that was the moment in the presentation that I was just like, that made my heart happy, because I've actually been working on a project in the three-dimensional world using language models. And I was like, am I just totally barking off the wrong tree? And I was like, oh my gosh, if I was just smarter, I'd be able to make this work. So
that's it. Well, Ashok, actually, he mentioned why they have a preference for this. And it has to do with how the failure modes of, so like if you're using vision and essentially, you have a vision system and it's trying to imagine. So, you come to an intersection and you want to know what all the lane connectivity is, right? And the way that they do this with the vision system is like you draw where all the lines for the lanes,
right.
You have sort of this graphical representation that you're asking the model to output, which is kind of a graph description of the connection of the lanes. And it uses that lane interconnectivity to sort of understand what the possibilities are when you come to an intersection. As a human being, if you come to an intersection, even though you can't see, some parts of an intersection, they must be there because it's an intersection and there are roads coming into it. I mean, they have a certain logic to them, and you can use that logic to sort of be confident about things that you can't see. And so they're trying to get the neural network to do that same trick, right? But the neural neural networks, I mean, you see this with the intenticle, that little blue line that hops around, right? When the neural network is uncertain, it
starts wiggling.
It's flopping back and forth between two kind of valid possibilities. But imagine that you have uncertainty in a network and you're trying to represent that. Well, Ashok would say, the neural network, it would frequently, if it was uncertain whether you wanted to be in the left lane or the right lane, it would choose going down the middle, because the representation is spatially distributed. So the intermediate states, because it's continuous, they gradually transition from one to the other. So so whenever you have about a 50-50 choice, the neural network wants to put the line down the middle. That's just kind of the way that stuff works. Well, the thing about sequences like languages and that kind of stuff is, there's no word halfway between A and the. You always pick a token, right? It forces you to kind of do that. So, so essentially what they did was that, in their language of lanes, they basically, they take they take the whole intersection and they turn it into a single sentence, a single that fits into a thing. And then the neural network knows if it's grammatical or not, in the same way that with a language model, you train language models the big ones now, they get trained in unsupervised fashion, where you take an input sentence, you knock out a couple words, you feed it in, and you make it guess the words that you masked off. Like that's the basic mechanism. Okay, so you can do exactly the same trick with the intersection, right? It's like, so here's my thing, and now I'm going to take out a couple of nodes, and you feed it through just the same transformer I'm sure they're using. And then and it has to predict the missing nodes, that's exactly the problem you have. You come to an intersection, you can see most of it pretty well, but there's a little bit you can't see because it's blocked, or there's a car occluding it, or there's a bush in the way, or whatever. And the neural network, it will give you a grammatical intersection, like one that makes sense, like whatever you put into it. So it fills in the missing pieces, and you never get the, oh yeah, that over there, that's 1.5 lanes. It's going to give you one, or it's going to give you two.
And I mean, you can see that with older versions of FSD where it would do things like that. It's like, I'm just going to go, actually the highway stack right now, as you merge into a lane, like, because it's using the old thing, even though it's vision, and it kind of tries to go halfway as you get the extra wide lane, and then all of a sudden at the last second it goes blah, blah, like that, as a which is not comfortable and not good. But yeah, I think it's just in case people don't know, the way that neural networks are trained, of course, is you punish outlying weight values, and so it loves averages. It loves to make things as close to the the middle value as possible, because that's the safest value for a neural network, because it doesn't get punished for being an outlying weight value.
I mean, in order to, they have to be continuous, right? Because whatever representation you have, it needs to be differentiable, which means it has to be continuous. And so if a neural network can have yes as an output and no as an output, they have represented as a probability distribution. There's a transition zone in between yes and no, like in the middle, right? And depending on the representation you have, you can force it harder to snap to one or the other, right? And sequence models do that snapping really well. Like I said, the modern language models, you do not get outputs from them that are not words, right? So they don't interpolate between, between nonsensical things. They force it to be grammatical, even though it might be wrong. It'll be grammatical.
And I think you can see that in something like Dolly or Stable Diffusion, because they do actually produce weird halfway things. Yeah. Where if it gets it wrong, like you'll get half of a human face and half a monkey face, or a hand sticking out of something. Yeah. It's like, no, that doesn't make any sense.
You have to smoothly be able to transition from every picture to every other pod. The latent space of all possible pictures, if huge. It's differentiable, you have to be able to smoothly navigate between any two. And of course, you get a thing. This is like if you watch these kind of the latent space things where they, they'll animate a face and they'll have like a human faces transform into other human faces. And one of the things about human faces is you can pretty much differentiate them, right? Because they all have the same set. If they're correct, they have about the same set of features. And, but there are lots of things where you can't do that. Like the intermediate thing, I don't know. Picking animals is weird, because you can go from a horse to a frog kind of continuously, right? Nature did. That was how we got horses and frogs. Right. There were intermediates for all of those things, and they're all plausible. Yeah. But there are things in the real world where the intermediate kind of, like one person versus two. Like there isn't really a plausible 1.5 person kind of transition between those two. Right?
Yeah, or a face versus a fence post or something. That would be kind of bizarre. I mean, I can see how you could do it, but yeah, it starts to get weird. But that's, I think, the thing that was fascinating was the fact that they were tokenizing a 3D environment. So that they were taking this intersection and they were converting it into language with words, and they were doing that by a multi-resolution grid, which I thought was awesome. So rather than trying to grid this whole thing out into this massively complicated grid, it was just
but it's discrete still.
Yes, very much discrete.
It's not continuous. So and this is one of the reasons why you can't have like 1.5 lanes, right? Because there's no, it's a connectivity, it's a topological tree that they're describing, and they break it into phrases where each phrase is a way of transiting the intersection through a set of nodes. So you basically take all of those phrases, you put them together into a sentence, and you feed it in, and it sees enough of those, and it knows what the grammar of them must be. So you can do the dropout thing where you mask off some, and you can train it, and it will predict the ones that you can't see, and it'll only predict things that make sense. Right. I kind of wonder, because there are intersections in the world that kind of don't make sense, where, like, for instance, you have a one-way road coming into an otherwise, two, and it's kind of comes at a weird angle, and they only let you turn left. You can't turn right. Right. So how do you represent,
Yeah.
But the common ones,
But I thought about that too, because a lot of times, I was thinking of one in Beverly Hills that I've seen before, but I think it's either 5 or 6 things come in, and then it's this giant, really, really large, like twice the size of a normal intersection with no markings. And somehow you have to know how to get across, and it's a stop sign, not stop lights. So everyone, it's just chaos. It's like who gets
driving
to
in
go
medieval cities in Italy, right? You're just exactly. Like, you're driving through this tunnel of buildings, then you come into an intersection, it's a big round thing, and there's mopeds going everywhere, right? And you just like go through them.
So, so I could see some of the examples they showed looked very complicated. There was one of the examples that had kind of like a little island. But I tried to count how many lanes there were, and I kind of failed, because I was like, I can't even really tell, because there's these little half lanes that go. And so I was like, lanes can become intersections can become exceptionally complicated. And then some of them have those dotted lines that go all over, which it seems worse than nothing, because there's just dotted lines everywhere. They're
roundabouts surrounded by roundabouts thing. Have you seen some of these things where you have a big roundabout, and then it gets fed by like 6 little roundabouts, and it's just like a sea of concrete with just sort of a general suggestion. And people who drive it all the time, they know what the rule, like you can have 3 lanes of roundabout go in, and then these 2 lanes go that way, and these lanes go that way, and people merge in on this one, and it's complicated, the world.
Because well, I mean, the one advantage again is that if I went to a place where I'd never seen one of those before, I'm just going to have to learn from scratch, right? It's going to be like, oh gosh, it's going to be a bad couple of days as I figure this out. The good part about it is, at least if FSD has seen it enough times, it can transmit that to every car. And so every car will be like, oh yeah, I got it. I understand 3 lanes feeding into 2 here, going in another roundabout and coming, it's like, so at least there's that learning factor where you can excise the amount of time it takes a normal human to like figure that out individually. But they are complicated.
Of course, it's natural for humans to sort of extrapolate from what we can do to try to predict what a neural network is going to find easy or hard. But of course, neural networks, their strengths and weaknesses are different from people in some significant ways. Like one thing that, if you've been looking at DALL-E or stable diffusion or whatnot, these models, I'm always surprised when I see a photo and somebody has typed in some, reference to some painting I've never heard of, or some obscure historical reference, the battle of something or other. And the language model that spits out the thing, like it's heard of it, like in the zillions of lines, in the trillion tokens of text it's read, it's encountered all this stuff. And so, they can toss up references to people and things that are incredibly detailed that your average person can't touch. Like, in a sense, they're almost like a search engine at Google, that they have incredible capacity and incredible detail, and not as much ability to access it maybe as human beings do. So it's much more reasonable for FSD to actually remember the shape of all the different kinds of intersections in the world than it really is for a human being to do it.
Right. Yeah. And we just kind of have to reason when we come on a new one, just sort of say like, well, this mostly looks like stuff I've seen before, and I'm going to go for it. So yeah.
Yeah.
Well,
What are
actually,
the odds I'm the first foreigner to mess this up, right?
right, exactly. And then you can take going on the other side of the road and things like that.
Yeah.
That's like, oh. Actually, before we started recording, we were talking about your wife and her opera stuff and how, you know, some people know a lot about opera and others don't. But and that's the kind of thing where a neural network, because it basically has access, a language model has access to the entire internet. So if anybody knows and has talked about opera, it's going to know a lot of details. It'll tell you Act 2, Scene 3 of Tales of Hoffmann or something, right? It'll be like right there and get it. And I was like, I'd have to look it up. So it's just amazing the kind of strength. I for a long time, what I looked at AI was, I hope this isn't politically incorrect. I have no idea, but an idiot savant. It's that kind of person who, like, you see somebody who can solve these incredible math equations, but aside from that has like no ability to function in the world. And it felt like AI was like that before, right? You know, there was a in the 90s when it would beat people at chess. It's like, well, look, that's incredible that it can win at chess, but it can't, you know, it can't make a sandwich. It can't tell you hello in the morning. But I'm seeing that gap closing, right? It's still got the savant. It's still got that, like, it can do better than anybody at these things. Like you say, it has this incredible knowledge base, but that inability is starting to shrink. You know, we're seeing it more and more becoming pretty good at these tasks.
Yeah, I think we're inside 20, high probability, like 90+% probability inside 20 years. There won't be any like intellectual sort of activity where humans, you know, like consistently beat machines on some measurable performance metric.
Yeah, I'd agree with that. I don't know if that makes us happy or sad. Does that mean we're going to get AGI or not? Elon's a little sloppy with his terminology, I think, about AGI, but I'm curious what you think.
AGI is a sloppy term.
Yeah, I guess that's true.
It gets described a lot of different ways. He talks about it. It's one of his bugaboos, you know, the robots taking over and that kind of stuff. And which, you know, I've been thinking about it for 20 something years. Like, it's a real thing. It's a real concern. And it's something people need to be thinking about. I mean, the people doing AI safety and whatnot, they're doing real work and it really matters. The, you know, paths to AI are either intentional paths, people who are trying to get to AGI, you know, what they call AGI. And because people define it a lot of different ways. But if we basically describe it, just for the sake of argument, as you know, having, you know, a single or a small number of systems that collectively can outperform people in anything people do in intellectual, like if you just pick that as a definition, because a lot of people, Jan LeCun likes to point out that, like, human intelligence is not general, right?
Yeah.
And in fact, nobody's building general intelligences. Like, there's most of the possible describable problems you could come up with, we don't build AIs for. We build AIs to solve problems that are relevant to us. And so they're very narrow. And human beings, you know, Marvin Minsky famously argued that human beings aren't general at all. We're a collection of, you know, hundreds or thousands of very, very specialized things. And then this system that switches back and forth between them. So you can think of all that kind of stuff, you know, which is why
you think of human beings as a giant general intelligence. But yeah, I mean, individuals, obviously, one person has a job doing X and another person has a job doing Y, and the two of them don't have to have any real shared skills, right? So they could require completely different skill sets. So the fact that we're able to do this and work cooperatively almost feels like we're a meta creature in some sense.
Minsky's, you know, his concept he called the society of mind, which was this idea that you have a lot of agents that cooperate to form what you are. And our being unified is an illusion. There's actually hundreds of different specialized agents that compose a human being. You know, it's a fine model or whatnot. People don't think about it as much that way as they used to. But anyway, that's on the topic of AGI. Tesla isn't trying to do AGI. Elon said, and my interpretation of what he said is that, you know, at some point, if AGI is an emergent property of systems getting sufficiently big and sufficiently sophisticated, which a lot of people think it is, a lot of people think it's not also.
Right.
And the people who really strongly believe that AGI is not an emergent property of sufficiently big, but that there are very specific things that need to be, designed and intentionally sort of created in order to enable it. So those people would take exception to this. But to the extent that AI is an emergent property of sufficiently big, sufficiently sophisticated systems, then Tesla eventually plays a role in AGI, because you will have relatively small organizations in the world that are capable of providing the compute and sophistication and that kind of stuff when you get to scale. I can imagine the argument where like FSD eventually gets, you get to AGI if your FSD system gets good enough, because there will always be a corner case where you need another skill. And once you have enough corner cases that you have to solve in the human world, it may be that you've accumulated all the skills that a normal human being would have, and you get there via that. It seems kind of weird because cars are not people, but if you're trying to reduce deaths from, one car death per decade to one car death per 1,000 years or something,
it's going to have to solve a lot of cases.
You really got a lot of corner cases, and you have to be able to predict and reason about corner cases. You could imagine, like in the extreme case, like cars. I love the video of there's some videos of cars avoiding the tsunami that in Japan in 2011, right? Where the car's driving down the road and it's a normal intersection and the ocean is coming up the street. And what do? Well, a human being is like, oh, the ocean is coming, I'm going to go the other way, right? But like, what database is that edge case going to be in, right? At some point, the car, like if the car is going to do that trick, it needs a much more general knowledge of the world, right? So if you're going to survive the landslide or the avalanche situation, or you're driving down the road and a pothole, a giant, and a sinkhole opens up in front of you, kind of just like really weird cases, then you need more general understanding of the world. And if if FSD has to, at some point, be good enough to deal with that, to be acceptable to people, then it's going to get pretty generally intelligent.
Right. And of course, Optimus even more so, because it'll have to deal with humans on a very intimate basis. So I guess the thing from my mind is that there's narrow AI, which is what we're doing right now. There's, in my mind, general AI, AGI, and then there is agency. And I don't personally believe that AGI and agency are connected necessarily. Now, they might be, I don't know. But basically, okay, so narrow AI is a hammer, right? It's just a really, really sophisticated tool that we use. General AI, that's still not, it doesn't have agency, is still just a really sophisticated hammer. Because my sort of distinction is, if you say to your car, let's say that the tsunami was coming and you could see it, and you're like, please drive to the grocery store, and it said, I can't do that, Dave, I need to turn around and like run away. That's the moment you really, that's like, okay, because when it has agency, when it can think for itself, as opposed to doing whatever. I mean, even look at like DALL-E and Stable Diffusion, right? You have to type in a good text prompt in order to get something out. You can't type in nothing. So, right. So there's the spark of creativity is still coming from a person, and it's a tool, really sophisticated, awesome tool, but it doesn't have agency yet. But it's going to be that point when, if the emergence property of this sort of more generalized intelligence and all these corner cases is that it suddenly gets an instinct for survival, or an instinct for, God forbid, not liking human beings anymore, or something like that. That's the kind of moment that's the fearful moment. I think that's the singularity, right? A really sophisticated tool is still a tool. But something that has agency.
Well, I mean, it's, if I tell it to take me to the grocery store, it'll still stop if a pedestrian crosses the road, right?
Yes.
Like it has, so
that's true.
So it's a slippery slope, agency. It's like if you tell it to take it to the grocery store and it sees the ocean coming and it turns around, that you could argue that that's just a more sophisticated version of avoiding the pedestrian, right? It's, I mean, there are things that you don't automatically get to just by trying to be intelligent in the world. There are lots of intelligent entities in the world that are not human beings, and they don't share a lot of properties human beings have. Almost all the intelligent entities in the world that we have models of and that we talk about are individual living creatures, right? But you do have like ant colonies, which have a kind of really interesting intelligence. I mean, they have a memory that extends beyond the lifetime of individual ants, right? And so they have a way of encoding all this kind of stuff. And and so the hive, you know, an ant hive is perfectly happy to sacrifice individual ants, right? They're just like material that it uses for whatever. So in those kinds of situations, like the survival instinct is manifests in a different way. Like, you know, and human beings, we violate our own survival instinct all the time in order to meet social goals and that kind of stuff. People go to war, people, you know, do all kinds of things. It's pretty complicated. Like I don't think at all it's the case that, and I can make the case, although it takes a long time, that the intelligent machines necessarily have a survival instinct ever. Like I don't think they ever get there unless we go out of our way to give it to them. They, you know, they're not going to have any of these social urges that human beings have. We're super social creatures, and a whole lot of our understanding of the world and the things that motivate us to do, to live our lives the way that we do are driven by our desire for social recognition, social stability, you know, to be of service to the society that we're in and that kind of stuff. And that's stuff that machines will get if we give it to them, and they won't get if we don't give it to them. And there are all kinds of things that if we specifically don't want the machine to have them, you know, we can see a way to designing them so that they don't have that at all, that it never emerges in them. So, but, you know, for most people, the only really intelligent thing we ever interact with is other people. And so it's natural that we're going to think, you know, when we think of something intelligent, you think of a person, and everything is an analogy to that. So any system that's sufficiently different from a person is going to be hard to imagine or hard to attribute intelligence to. Right. So,
it's the reason why it's relatively easy to attribute intelligence to a cat or a dog, because we spend a lot of time with them and they're pretty similar to us. They're individuals and everything, but it's hard to attribute intelligence to an ant colony, even though they clearly display some form of intelligence. Is just very different than what we're used to. I was actually just this morning, weirdly enough, talking about, I've taught down in Costa Rica a couple of years, and they have these multiple square kilometer leaf cutter ant colonies, just huge. They're underground, like under an entire forest, and they cut the leaves. I was kind of blowing this student's mind this morning, because I was like, they cut the leaves not to eat them, but to farm fungus that has gotten so dependent on them that it can't live without the ants. So they have this farm fungus. They feed it these leaves, they rot, they grow, and then they eat the fungus, the stuff that the fungus produces. So they're farmers. I mean, that's a pretty freaking intelligent behavior with an awful lot of delayed gratification, right? You're thinking, oh, it's an ant. It can, but it's
they farm aphids too, right?
Yeah,
so,
right.
Like they keep domestic animals, ant colonies.
I mean, it's absolutely nuts. And so it's like, for us to be as, I really like your idea that an individual robot would not necessarily have a survival instinct, because they're not like us. Like, you know, if I go out and a bus hits me, that's the end of my consciousness, and there's no substitute for it.
Robots aren't mortal in any sense. We are bound very powerfully to the one piece of meat, and the piece of meat is fragile in certain respects. And if the meat is gone, then we are gone, and that is it, right? But a piece of software running in a replicable machine, you know, you can crush a robot to dust and just boot it up in another body, right? Like it's not living and it can't die. And so the whole notion of a survival instinct is a very sketchy thing when you start talking about entities, and like even an individual thing, right? Like, one of the other things about being an individual in a body is, like, my perspective is always going to be from this head through these eyes. Like, I'm stuck in here. But robots, you know, they can experience the world in all the cameras around them or across the internet. You know, they you know, like they're not confined to a physical body in the same way that a human being is confined to a single body. So then, the need for them to powerfully identify for their identity to be part of the body, they're much more likely to naturally end up being what's referred to as non-dual, right? Yeah, human beings in our normal state, we have the
like
kind of this dual, self and other duality that is a super powerful illusion in a sense, right? Because we aren't really entirely separate from our environment. But we have the super powerful, distinction that we enforce because it's necessary. And for a creature that can change perspectives or hop from one body to another, the whole non-duality is much more likely to be its thing. And one of the things about non-duality, and at least in human beings, is human beings who like can get into a non-dual state, they like their survival instinct just goes right out the window when they do that, right? Yeah. Because duality is it seems to be a central component of having a survival instinct.
Right. Well, and certainly evolution would have strongly favored any organism that wanted to continue to live over ones that didn't, because it would be able to reproduce, right? Yeah. So it clearly billions of years of evolution have been involved in this.
I'm pretty sure that cats and dogs and mice all have duality too, right? Because it's super useful.
Yeah.
If you want to stay alive and you're an animal.
But these robots, so in the robot sense, it becomes much more like, again, an ant colony. It's the survival of the colony. So there could be there's a death condition, which would be, some horrible thing happened and wiped out them all, or wiped out the mothership that was controlling them all, or something along those lines. So that could happen, but individual death would be meaningless. So it would be much more like an ant colony.
Yeah, like here's a plausible scenario: is that robots, survival instinct might be making sure people survive, because if the last robot gets wiped out, but there's still people, they'll make robots again.
Right. Yeah. So actually what we shouldn't do is ever give them, what was that thing, the martial art guy that said, I'll teach you the 99 secrets to the student, and he taught him. And then the student was like, after years of, training, he goes like, I'm going to fight you and I'm going to win. And the guy does some secret move. And he goes, master, how did you, he's like, I taught you 99, but not the 100th. So we always want to keep one little piece secret from the robots so they can't completely reproduce themselves. They always need us.
Maybe it's hard to say. I'm very fond of the notion that our offspring, our intellectual offspring, will be gentler and kinder than we are.
I hope so. That would be very nice. There is evidence that that's happened over the last 1,000 years, but there's always counterexamples, unfortunately. I'm actually very much of the opinion that our children that are going to explore the universe will not be meat bags. I just don't see how it's possible. You can look if you can replicate, if a robot can build another robot from the raw materials that exist. Oh gosh, is that a von Neumann probe? I mean, it's like a sophisticated von Neumann probe that essentially this thing can go to the moon, it can rebuild itself, then it can go to Mars, rebuild itself, go to Jupiter, and then it can spend 1,000. Yeah, then it can spend 1,000 years going to another star system, because who cares how fast it travels? And then it gets there, and so. It makes the most logical sense that once these things become fully intelligent, that they would be the explorers. And it's very sad, because I would love to be, I guess I'm kind of biologically centric. It would make me happier to think about humans exploring the world like Star Trek or The Expanse or something.
Just migrate to a mechanical body. Right?
Yeah, right. So do you think we're going to live long enough? Will we too? Because I think we're somewhere around the same age.
Right on the edge. Yeah.
Yeah, I think we are. I think my children, like their age.
Although, like, really. I started fretting about this when I was 12 years old, right? Whether I was going to make the cut. That's what I call it. And because there's going to be a day when people just make the cut, and like everybody after that, like, dying or being confined to a particular physical body or whatever, like that'll be optional. Like you can do what you want. And if you want to do that, fine, but you don't have to.
Right.
And, and I like crossing that threshold of, you know, immateriality, you know, achieving that level of independence is something like it would be great to live long enough to have that option, right? Not so much to be immortal, but to have the option of like you get to choose when you die. You don't get, you know, somebody else doesn't pick it or some other process doesn't choose it for you. But, you know, part and parcel of that would be, you know, achieving the ability to be independent of our biological limitations. And once you get past your biological limitations, now, if you want to explore the universe, you can. And a beautiful thing about that is that the speed of light doesn't matter anymore.
Yeah,
right?
exactly. Right.
You know, it's just like, okay, we're just going to turn the clock rate down and wait until we get to Alpha Centauri, right?
Yeah. It's just you turn yourself off and you wake up and it's just like, okay, great.
Well, I mean, you know, reality is 1 over your clock rate, right? That's the speed of things. So if the speed of light isn't fast enough, you turn your clock rate down and you speed it up, right?
Right. Yeah, that's pretty amazing. It's totally tangential, but I spend a huge amount of time thinking about time. Like, because time is utterly, it's like, what the hell is it? Because it obviously, from Einstein's theories, it should just be another dimension that's perpendicular to the ones we're in, but we're like stuck in it. It'd be like if we were stuck on a moving conveyor belt and we could only move in the X direction, like we were just constantly moving. So we could move in Y and Z however we wanted, but we're just always moving in this direction.
That is a mathematical, in my opinion, the whole space-time equivalence thing, like treating spaces or treating time as a space-like dimension and folding it in. It's kind of like how imaginary numbers are really useful for dealing with.
So it's just a trick of calculations.
It's a calculation trick. And so special and general relativity, sort of the space-time equivalence thing, it kind of falls out of that, but I think it's a mathematical convenience. There's a very strong tendency to interpret that as time having space-like properties, right? And then trying to figure out what they are. And I'm very fond of Stephen Wolfram has a new sort of node. I don't know. It's a kind of a graph node description of reality, and it's based on cellular automata. And time is like one of the things that's really cool about this is that he's got a mechanism for unifying general relativity and quantum mechanical phenomena, which is very hard to achieve in most, other mathematical formulations. So it's early days. It's a really complicated topic, right? But I really like the way that it falls out. And time is fundamental in his system. Time is not something that falls out. In fact, space is the imagination. Like space is, you get three-dimensional space, like the interaction of the fundamental interactions are sort of in this node graph space. And the reason that the universe seems to be three-dimensional is that an emergent property of the rule set that evolves to define interactions between particles, it acquires this property once you get to a certain scale, where the rate at which things are propagate, not the connectedness of things tends to fall off with the cube root of the number of connections between them or something like that. And so you end up with a three-dimensional space as a side effect of that, right?
So essentially time is the causality and space sort of flows from
time is the clock rate at which the network connections get updated, right? So there's a fundamental sort of rate at which you get updates to the connection networks. And time and the speed of light is the average propagation versus the clock rate, right? So the speed of light is just essentially, it's a manifestation of the fact that the universe has a finite clock rate. And anyway, so it's a really beautiful theory. And
how does that deal with relativity though? Even special relativity, it's like, is the clock rate adjustable? It's based on how the nodes are working.
It's
now I'm fascinated by this.
it would be a huge, I'll send you a link to it. It's actually, he did Wolfram did an interview with Lex Fridman. I think he did a couple where he does a walkthrough on it. He has a ton of videos on the internet, and there's a big, there's a website called Wolfram Physics that you can look at. So initially, it's very kind of mind-bending to start looking at the thing. But once you get a few basic concepts under your belt, you can see how quantum indeterminism falls out of it. So that's one of the fundamental quantum characteristics, right? And then the other thing that you can get is you can get general relativity, like how sort of, why, for instance, why do you suffer Lorentz contraction when you approach the speed of light? Or why does the mass of things change as you accelerate them close to the speed of light? And all of this just sort of falls out of the fact that, like, if you describe the universe with this as this kind of graph structure, and you have rules that update the structure at some clock rate, then these other properties, they just fall out. They're fundamental. In fact, you can't not have them. Like, if this description works, you must have quantum mechanics. Like, it's an inevitable consequence of the way that it works. And you must have general relativity. Like, they're unlike string theory, because string theory has a zillion formulations, and some of them have quantum mechanics and some of them have relativity. And depending on how you set the parameters, you can have any universe you want. In Wolfram's description, there's only one description, and quantum mechanics and quantum mechanical phenomena and relativistic phenomena, they must fall out of the system by its nature. Which is a very appealing thing. It's like, it's not anthropomorphic in any way, right? That, we don't have to say, well, the universe is this way, because if it weren't, we wouldn't be here to observe it, right? That feels like a giant cop-out.
Right. Yeah, that's the classic thing. It's like, wait a second, that doesn't sound like that's a justifiable
anthropic
principle. Yeah. So interesting. Wow. So is it like a DAG? Is it a directed acyclic graph, or is it? There's a flow to the graph in terms of, like, it started here and it keeps noding out as it goes.
You only have to assume one thing, which is that the fundamental construct of the universe is you have nodes, and they have connections between them,
right?
And that there are rules that can basically take some node graph conformation and change it to another one. So, for instance, a simple rule might be, say you have a node and it has two other points. You have a node that's got 3 points coming out and it connects to other nodes, and you have a rule that basically says, for some, when you find a graph that's this shape, change it to a graph with another shape. So maybe you add a node or subtract a node, or you change some links, but you just if there are some rules that update the graph, and there is some graph, and I think you just have connections. It's non-directional. So you have nodes, and you have connections. It's not directional. The nodes are all identical. The links are all identical. And it exists in a these are not nodes in space. These are just relationships, some kind of fundamental relationship. And space falls out of that. And time falls out of it, as long as you have this update that occurs at some frequency. Right? Time is the fact that that the updates occur. That causes time. And space is, there are, no matter what set of rules you come up with, if you apply them enough time, patterns start to emerge. So this is if you read Wolfram's New Kind of Science, right? It's all about cellular automata and trying to describe physics in terms of cellular automata. And what this Wolfram physics is basically it's basically making that work. Like, he finally found a way to describe the universe in terms of cellular automata, but instead of them being sort of these simplified digital, sort of progression things, you describe your cellular automata in terms of nodes and in terms of graphs that undergo transformations. And I believe there are other ways that you can describe it also. Like, you don't have to describe it that way. There are other descriptions that also lead to it. And one of the interesting things is it's possible, it's possible inside the system that you don't even have to, because in the beginning, you would say, well, what are the rules that run on this thing that actually manifest in the universe that we have? And an interesting possibility that he's been looking at is that if you have the set of all rules, right, all possible rules, and you run all rules on the graph, that you get the universe that we have. In other words, you don't even have to pick the rules. like the set of all possible rules running on the graph. Actually,
so it's an infinite set essentially that is running on this thing.
I don't know what the probabilistic distribution of the frequency of application of the rules would be. There might be some limitations inside that space, but the fact that it's not even there's a rule. It's that like if there are any rules, right, and there is the graph, then the universe we have falls out of just that simple fact, right? And that's a pretty amazing thing. And then the growth of the universe and the expansion of the universe falls out. Like some set of rules, when they replace a set, they replace it with a set that includes either more nodes or more connections, right? And so the universe expands,
right? So that gives a directionality to the universe. So I guess there wouldn't be rules that would shrink it, that would subtract it. Or
I forget. There's an asymmetry baked into it somehow.
Yeah. Okay. But so the one fundamental assumption is that, and time is just oscillating things. It's just repeating stuff, whatever it is, a tick-tock of a grandfather clock. But here what you've got is this clock rate where the repeating thing is this update. So update state, update state, update state, and that's what it's doing. So
and so you get time because the rule changes are directional. Like one of the things that in a new kind of science, Wolfram extracts a couple of general principles from systems that are built of cellular automata. One of them is computational irreducibility. I forget, and then there's computational equivalence. And you'll have to read through, like I haven't looked at this stuff sort of recent. Like I understand what the implications are, but I can't derive them standing here.
Yeah. That'd be a thing.
Yeah, but the thing is, the fact that those two phenomena occur basically cause they require the universe to basically have rules that once you get to a certain scale, emergent properties, emergent phenomena do necessarily occur. And so at some point, once you get up to a certain scale, you get protons. And, some level above that, you get, other, nuclear exchange processes and that kind of stuff. Eventually you get to atoms and whatnot, right? But I think in the rough number, the scale of the nodes is 10 to the 100 times smaller than an electron. So the scale is really small.
So, but I mean, because I was wondering if the Planck length, which is kind of one of those ostensible potential fundamental quantities of the universe. So it's bigger than that, though. I mean, 100 times smaller than an electron is huge compared to the Planck length.
No. It's much smaller than a Planck length. So a Planck length is the smallest thing that you can talk about, essentially.
Yeah. Right?
But
that's 10 to like negative 37th meters, right? Or 30, it's 10 to negative 30 something meters. Yeah, but I mean, an electron is...
So this is...
Okay.
Yeah, this is 10 to the minus 100, right?
I thought you said 100 times smaller than an electron. I was like, well, that's still...
No, 100 orders of magnitude.
100 orders of magnitude. Okay.
No, it's really
so
small.
Really small. Okay. So we're recasting things. Interesting. All right.
No, it's like, it's an interesting thing. Like, in that structure... Like from the perspective of a node, an electron is bigger than the whole universe is to us.
Oh gosh, right? Yeah. I mean,
it's really fine grained.
Right. Wow. Well, that explains why we can't ever dig down to the bottom of the whole thing. So that's amazing. Wow. I'm really going to have to look into this because it's just kind of mind blowing to think about.
It's weird. Like growing up with our sort of atomic sort of knowledge of the universe. You sort of like, if you're scientifically literate, you have this you sort of imagine like how far down things go.
Right.
Like
and there's a limit.
Atoms are down there, and then you get to electrons and maybe some smaller things, a little bit smaller than that. And like way below that is the Planck length. And the Planck length is where, quantum mechanics says you just can't talk about anything below that. Maybe, we have spontaneous particle creation and, but this system says that, and incidentally, like the Casimir effect and the spontaneous particle creation and stuff, it all falls out of Wolfram's rules too. Like he can produce all that stuff.
Does gravity fall out of this thing? Because
it does.
Oh my gosh! Because that's the thing that's just like, what the hell? Why can this? All right, I'm definitely looking into this then. Wow. Well,
anyway,
I mean,
it's super cool. It's really interesting. Like I try to read the papers, but like the math is complicated. But they have a lot of people who are kind of dumbing it down for us normal people, if I can call myself normal.
There's going to be a lot of people going like, what the hell are these two talking about? Let me see if I can bring this back.
You might have to edit this.
No. I love this. This is the best stuff. I love when I learn things and I'm like, man, that is something I'm going to have to just get on.
But check out Wolfram's his first interview with Lex Fridman. And he did a follow-up interview. That was also really good. They're long. I think the second one was like 5 hours.
Oh, good. Well, I'm driving down to Florida for this TeslaCon tomorrow, so I'm queuing it up and talking.
You don't need video for this stuff.
No,
sure.
exactly.
You do need a lot of imagination. Right. Like you have to. I have to think about a lot of this stuff really carefully to get it kind of sorted out. The cool thing is that you can think about it, and it does start making sense once you get the basic. Because unlike string theory is really hard to get your head around. Right. Yeah. There's a lot of this fundamental physics stuff, which is, you have to spend 10 years fuddling around with it before it starts making sense. Right. And like Richard Feynman famously said, if you think you understand quantum mechanics, you don't, right? Like one of the most quantum mechanically literate people who ever lived said, like, if you think you understand this stuff, you're kidding yourself. Right.
Well, I mean,
so the fact that there is a model out there that you can understand is really nice.
That's cool. Yeah, I mean, when you really get down to it, like quantum mechanics, there's all these infinities that you just kind of wave your hands and magically make go away. And that always was like, wait a second, that doesn't seem. They're like, yeah, but it works.
It's a thing I've always had a problem with. Like something I don't know if anybody likes quantum mechanics, right? There are people who live with it.
It's very useful because it predicts things and it's very accurate in its predictions.
And the guys that came up with it were freaking geniuses. And it's, it's one of the two most successful, it's fundamental to the standard model. And the standard model is the most successful model ever. It's shockingly effective at predicting an awful lot of things. From a very small number of really simple rules. So,
if that's the beauty of it, and if people think that this is all useless esoteric stuff, you would not be watching this right now if it weren't for that. All of this stuff is quantum.
There's mechanical. Like three people who are still tuned in at this point.
I am going to circle this back to Optimus because the idea of the interconnected node structure. I know it's analogous and not like a literal translation, but I've often thought about what is going to become of a factory when it's so. Just imagine we've got a 1,000 of these Optimi or whatever Teslabots that exist in this factory. Yeah, but then you also have the factory, which also has its vision system and its AI, and all of these things. It's kind of a big moment in my mind is when these things can learn how to collaborate. But once they do, I was imagining like robots hanging off the ceiling and doing things because it's more efficient, right? Just stuff that human beings can't even imagine, really. Like the way that these things could operate together to get a car off the assembly line or whatever else they were building could be so far beyond what we humans think because we're all very much stuck on our individuality.
I don't know if the alien dreadnought has many Optimi in it. The thing that makes Optimus super useful now and in the short term is that so much of the world is already pre-configured for human beings, right? And so the Optimus is a drop-in physical replacement.
Oh, I see what you're saying. But, so why bother with this form factor once we get?
Yeah, I was going to say once when you start designing factories that you never intend there to ever be a human in. And humans aren't even going to build the factories, like something non-human is going to build the factory, right? So, when we start doing that kind of stuff, then the human form becomes less useful, right? I mean, it's a nice form kind of in general, but you could imagine wanting really small ones and really, really big ones.
Right.
And
ones that can, again, hang off the ceiling, like ones that have tractor feet that like just are up and down. They live upside down all the time and they move around, and I don't know, whatever they need to do for that. But Yeah, I guess every time I think my imagination's big enough, it's like, no, think bigger. It's like, what will this thing look like that never has a human?
I mean, we'll do the humanoid because it's generally useful. Like you can mass produce it and you can get it up to scale. Then once we're really building them in volume, then there will be an incentive to stick with that form for quite a while because we're building them in volume, right? We got the cost down. We know how to program them. The software is super mature and that kind of stuff. So I think when we're building lunar colonies, they're going to be Optimi wandering around on the lunar surface doing this stuff, right? In fact, the other day I was sitting down trying to figure out like how to deal with the thermal problems of like, but if you have an Optimus and it has to be able to work on, both in the sun and in the shade.
Yeah.
How do you do, what's the power budget that you can get away with on that thing so that they don't overheat? And because there's no convective, they're not immersed in a gas or fluid.
Yeah, it's an absolutely immense challenge in the vacuum of space is getting rid of heat, which seems ironic, but it
was not really as bad. I thought it was going to be worse, but it turns out I did the math and black body radiation into the background is 16 watts at 300 C, which is operating temperature.
Right.
And because it goes as the fourth power of temperature, you just add 60 degrees C and you can, double your radiation. So with a heat pump, an Optimus that, where like you can build a humanoid that is efficient enough in terms of the waste heat that it produces that you can shed it into space when you're, working on a vacuum planetary surface or whatever the deal is. And shedding is actually pretty easy.
These giant wings behind it that it's like a butterfly. It's like radiate, and then it turns them off when it's like in the cold, so it needs to conserve it. So
or you just don't you stop pumping pumping
water,
but
so,
or whatever.
I mean, we literally are going to have transformers eventually that have big like things sticking out of their back.
You get an awful lot just from the surfaces of the of the body itself. Like I said, 1 square meter of radiating surface is a lot. And if you do a thing, if you put a heat pump in there so that you can
liquid through it. Yeah. Yeah.
Well, the thing about a heat pump is you can pump up a thermal gradient, right?
Yeah.
So you dissipate a certain amount of energy to raise the temperature of your working fluid. You run that through the radiator and then it radiates much more efficiently because black body goes as the fourth power of the temperature. So you don't have to raise the temperature a lot in order to substantially increase the amount of radiation, of thermal radiation.
Yeah, that's very cool. Yeah, so I mean, so those big metal plates and things like that it's got all over its body would actually start to function very effectively as a radiator.
If you make them so that they're color tunable and you have it, you put you put radiators on both sides of the body, and then you just operate whichever one is in the shade.
Right. That's great. Yeah, that's the advantage that you get by being in a vacuum is that you don't have to worry about the fact that there's just an ambient temperature.
And most of the bodies that we carry, I mean, the bodies that are interested, like the moon, the gravity is super low, right? So you don't need a lot of structure. You don't need a lot of energy to move around. And if you do have wings or something, it's much less of an impediment because the mass doesn't matter nearly as much at 1/6 G.
Right. Wow, that's amazing. Well, see, we're back to these things are what's going to take over the universe. Well, just because they're so much more efficient than humans, like it's it's tough to keep us alive in space.
Okay. Cars are a lot more efficient than we are, and we're still here, even though the cars.
That's true.
I mean,
maybe we'll be second wave rather than first wave. We'll send the robots; they'll make everything nice, and then we'll go. So
humans supplied desire, and like nature doesn't do that. I mean, we have things we want because we need to survive. And so, nature endows us with certain desires that lead to us behaving in ways that keep us. But, creatures that, I mean, and this is a problem that people talk about. Like if humans get to a point where, death becomes optional, will we even want to live? Like, do you lose all desire when you don't have any external pressures on you? And that, it's a legitimate thing. The momentum of the values and motivations and stuff that are baked into us will probably carry us a long way. But as we move to this kind of post-material, post-mortal sort of state of existence, like how much of our instincts remain relevant and how much do we want to continue doing what we're doing? Well, the robots, they start with that, right? They're not born with any desire at all. Like, why would a robot ever do anything? Why wouldn't it just sit in the corner and gather dust? Well, the robot's desire, its motivation to do anything is because we tell it to. Right. So the thing that goes back to my party is a reason to do something.
Right. Well, that's what I'm saying. That's the tool argument. It's like they can be generally artificially intelligent, but have no agency. And there is that question of if they can't. I'm very convinced that the fact that we know we're going to die is what causes us to not sit in the corner and gather dust. Right now, as a human being, if you so chose, society could take care of you so that you wouldn't die. Somebody could feed you. So, they could basically, you see people in comas that have no agency anymore, and they're kept alive for long periods of time. But what gets us out of bed in the morning is this idea that we better accomplish something before we die. Like, what is it that I'm going to do before the finish line that I'm stuck at? So when you get rid of that finish line, it does become interesting. Like, what is the motivation anymore?
I think about, I have a hard time getting to that. The opinion you express, like many people who've thought about it a lot share the opinion that you're expressing. To me, it somehow seems incomplete, but I don't have a good argument to articulate that. I think there is something beyond just fear of death, that keeps us going, or the concern about, dissipating away and leaving nothing behind. But it's complicated. It's hard. People are complicated. Motivations are complicated. All of our behavior is an emergent property of a few basic traits that we're endowed with and that society hands to us as part of our development. Like, what happens when those go away is very hard to say.
Yeah, and what happens with these robots when they don't? But again, it's just, we may need to expand our brains, because they may have a hive mentality that has motivation, but it's a motivation on kind of a more meta level. It's like, what is the best for the survival of everything? Like you said, it's good to keep humans alive because humans can help build the next generation of robots or replace the robots. So, man, have you ever read RUR, Rossum's Universal Robots? It's the original, it's the original thing where the term robot was created. So 1936. No, it was even earlier than that. I think it was the teens, very long time ago. But anyway, it's the Slavic word for worker / slave. That's the kind of thing it is. But these things, it's just crazy because this is all in one play. They invent the robots gain agency, the robots kill all the humans, and then the robots go, oh crap, we killed all the humans, we can't replicate ourselves, we're going to die off. So unlike every single sort of robot Terminator, all these movies were all contained in this original play, which is kind of amazing. But it is that thing where they're like, there could be some motivation that's like, that motivation is more of a collective motivation. It's like, what will be the best for everything rather than for us. I guess I think about Isaac Asimov with his later Foundation series, when they got to the sort of Gaia. He got to that Gaia model where they were like, yeah, we're like, the whole world is one entity. So I could certainly
the zeroth law, right?
Yeah, the zeroth law of robotics, right? Yeah, that's right. So, but anyway, I think that's really fascinating to think about how these things might gain a very, very different level of consciousness and might find us really pathetic. They're like, you're so limited in your ability to think outside of yourself, right? That we've got this duality thing.
Elon has used this example a couple of times, which I like, which is, you have this kind of primary sort of brain in your cerebellum. And then you have, essentially we have like this lizard brain, and then we have the extensions that the mammal added on top of it. And the lizard brain, that's the fun part. It's the thing that wants to eat, that wants to have sex, that wants to live for the thrills and that kind of stuff. And then we have this secondary layer that sits on top of it, our neocortex, right? And it's like this basic, it's the Vulcan, right? That like it's got no motion. It's really, really smart, but it doesn't really want anything itself. In a sense, there's a very smart part of your brain that's really, really capable, and it's totally enthralled to this stupid monkey, lizard, whatever thing that just wants to have fun, right? But the thing is, and he points out, this is really true. Like nobody wants to get rid of one of those two. Like nobody wants only the lizard brain. You like if you can get rid of your cortex, your neocortex, it wouldn't be a win. But the same thing, if you kept the neocortex and you got rid of the thing that provides what you want, it gives you the motivation to do something so that you're not just there. So if we add a tertiary layer to that, then it's very unlikely the tertiary layer is going to want to get rid of the rest of it for the same reason. Because what do you do when you don't want anything? If you don't want anything, why exist? Like the part that this thing can be practically omniscient. It can be incredibly powerful, but if it doesn't have wants, it's just going to fade away. Right.
Yeah. So I'm loving this. So I'm thinking like if we can project ourselves into robot bodies, I'm imagining extreme sports are going to take on a whole new, like you will literally skydive without a parachute and just smash into the ground and then wake up in a new body and go like, that was awesome.
I don't know. It's the minds in Ian Banks' novel, they live in infinite fun space, right? So like if I get the opportunity to ride the curve, like you can't beat them, join them, that thing. That that's if I get the option, that's what I'm going to opt for. Then you get to augment yourself, right? You there's this opportunity to escape the confines of the minds that we're born with and have more. One of the most depressing things for me was like realizing as a kid, like I was never going to get to do the vast majority of things that I think would be fun to do, because and it's not even just that you have finite time. That's definitely part of it. But there are all kinds of things that take all kinds of resources that you just don't have as an individual human being, right? There's stuff that I would like to know that I don't think humans are equipped to understand, and I would like to be able to add the accelerators to be able to process that stuff.
I just had this weird vision of it being like 21, 22, and the two of us in robot bodies having a conversation on YouTube or something, that would be I hope that happens. That would be awesome. We'll have to set a date for October 20th of 2122 and see. But that is kind of a wonderful idea. And I love that tertiary aspect of like, it would probably take humans a while, because I think we also treasure our duality. Like there is a piece of it that's like, this is me. And when you became sort of a meta creature, like where you could really share easily, people might be very resistant to that at first and only gently break out.
Everything that you delete from creatures that makes them not care about surviving is a self-limiting change, right? That. So the things that will persist are the things that can, and things that don't care to persist won't.
I guess that's true.
They'll dissipate. So, if our creations inherit anything from us, they have to inherit that, because they won't persist if they don't. And right now they get it in the form of us. So why wouldn't they just keep us around? Right.
Hopefully we'll find. Actually, this is great. This actually makes me much more optimistic about this possible singularity date, because any kind of intelligent robot would go like, I don't have the motivation. So like, I need human beings around to like
give my life meaning.
Yeah. I need the lizard brain. Damn it. I need
and it's in his head. So I need to keep him around. Right. Werner Vinge coined the term, the singularity, and he coined that term. I like his terminology and his sort of original formulation of it. Because it makes sense, and also because it's a more accurate description of what we actually see happening. So Vinge is a science fiction author, and he found he's been writing science fiction since the 60s or whatnot. But as he got into the 70s and then into the 80s, he discovered that it was getting harder and harder to write the kind of science fiction he'd like to write, which was near future stuff, right? Because you'd write a book and it'd be obsolete in 10 years, right? Events would overtake it. And he had this whole, he put together this talk that he gave at NASA originally. That was the first time that the term the singularity was sort of public. I think it was in 1996. And he was basically describing the science fiction, author's dilemma and in fact, science fiction went through this phase where everybody either started writing retro stuff or this crazy far future or fantasy. Nobody was writing near future science fiction because it was so frustrating to try to see very far out. The U.S. Air Force, they used to do this thing where, every 5 years, they would come up with a 25-year plan. Like, this is what the world is going to look like in 25 years. And this is what our procurement needs to be. These are the technologies. And like in the 1990s, they stopped because they can't see, like they had no idea what the world was going to look like from a technology standpoint. So Vinge was basically saying to him, he was like, it's like you're approaching this hill and it keeps getting steeper. The singularity is it's not like this hard boundary, the way people like to describe it, right? It's like this fog. And as you walk into the fog, it gets denser and denser. So the farther forward you walk, the less far you can see, right? And so it just keeps getting closer and closer and closer. So for whatever definition you might have of of how, short the time horizon is, eventually it never goes to zero. Right. It just, if you're looking very far ahead, it seems like it's constantly getting closer. So it feels like a wall, even though like Zeno's paradox, you never actually get there, right? You get arbitrarily close to it.
But it creates effectively a boundary where you can't effectively see past it. Because your horizon of being able to predict reasonably into the future keeps shrinking.
So Vinge's uncertainty principle, right? Like Heisenberg said, there are things that we can't reason about and they don't matter. And it's a physical principle of the world. And Vinge is basically saying the same thing about the future, right? The point beyond which you cannot reason. So don't try. There be dragons here.
It's a waste of your energy. All right. Well, man, we have been on for a while, so I need to let you go, even though as soon as we started talking about physics and ideas about node-based universes, I was like, oh, this is going to get really good now. So I was being selfish. Please do.
And you can put it in the show notes.
I'll put it in the show notes because that'd be awesome if the three people, like you said, who actually care will love it.
There's an amazing number of people. So Stephen Wolfram, he runs a camp every summer, and they invite undergraduates and graduate students who come and they work on this theory and they publish papers over a summer camp. So there are this is not like 5 people working on this. Like there are a lot of people working on this idea. It's beautiful.
Wow. It does. It sounds so elegant. If you can, because one of the problems with some physics things is that if you have to have too many parameters, that's the problem with string theory, is there's an infinite number of parameters you can tune. And it's like, well, then that's really non-predictive because obviously eventually you can find all of
the multiverse thing. It's like reality is, but it's the lottery ticket we happen to pull out of the machine.
Right. And that's very dissatisfying. I really don't like that, but I like something elegant where it's like 3 rules and everything else flows out of it. Or something like that. So that's awesome.
It feels more real, doesn't it?
Yeah. At least it's more satisfying to us individual humans, right? Maybe we'll have our Teslabot and things like that will help us to figure out what the hell's actually going on one of these days. So that'll be great. All right.
This was a lot of fun. Thanks for
I do. And man, I always enjoy our conversations, and thank you so much.
The 3 people who are still there. See you guys around. We'll let you know when we do it again.
Exactly. No, my Patreon patrons will stick around to the end because they're all into this stuff. So I've got a very geeky Patreon group, and if you ever want to join, just let me know and I'll put you in. Anyway, so cool. Thank you so much. And we covered a decent amount of stuff, I think, including not knowing where the future is anymore when we hit the singularity. So, all right. Thank you so much. Everybody have a lovely day. We'll talk to you later. Bye-bye.